state variable analysis in the discrete time domain. Earlier in our videos, we have studied the state variable analysis technique for the continuous time. Now here we will study about the state variable analysis technique in the discrete time domain, how we are going to represent the state variables, the input variables, how we can derive the state model and the state space equations all in the discrete time domain. So let's start with our topic. Now, what are the situations where we use the discrete time domain analysis? There can be two situations. First situation is that we are dealing with a system which is having discrete signals. That is the signals which are changing with time. So if the signals in the system, they are discrete time signals, then we have to do the analysis techniques in the discrete time domain. And the second situation is that the system, it is having the elements in it, and these elements, they are continuous time elements, but at some time the signals get converted into discrete time signals. So whenever we have these type of situations, we will use the analysis, or we will do the analysis in the discrete time domain. So these two situations are: so if the system is completely discrete with respect to time, or the elements of the system are continuous time elements, but the signals at certain points are in discrete form. So in these two situations, we do the analysis in the discrete time domain. Now in discrete time domain, how we can do the state variable analysis, how we can choose the state variables, or how we can represent the state model of the system and can derive the state space equations. So we have studied in our earlier videos that in continuous time, the state variables, they are represented like x1t, x2t, x3t till xnt. So these are the state variables in continuous time. In discrete time, the state variables, they are represented like x1 k plus 1, x2 k plus 1, x3 k plus 1 till xn k plus 1. So these are the state variables in discrete time. Now comes the input and the output variables. In continuous time, the input variables were u1t, u2t, u3t. In this way, we represent the input variables in the continuous time. Now in discrete time, the input variables, they are represent like u1k, u2k, u3k. In this way, we will represent the input variables. Now comes the output variables. Output variables were u1t, u2, y1t, y2t, y3t. This is how the output variables are represented in continuous time. Now in discrete time, it will become y1k, y2k, y3k. In this way, we are going to represent. So these are the changes in the discrete time. Now comes the state model. In discrete time, in continuous time domain, the state model is represented like x dot equals to axt plus but. This was the state model in continuous time. Now in discrete time, the state model will become this is the derivative of the state variables. So here it will become x k plus 1 okay, and this output equation so this is the changes in the discrete time domain. Now here these matrices A, B, C, D and xk and uk. Xk is the state vector, of n cross 1 order. Yk, it is the output vector. P cross 1, it means it is having p components. N means this state vector is having n components. Now uk, it is our input vector. M cross 1. So there are n state variables, p output variables and m input variables. And these matrices A, B, C, D, A is our state matrix, B is our input matrix, A is the state matrix, B is input matrix, C is output matrix and D is the transmission matrix. So this is how the equations they are represented in the discrete time. This is our state equation and this second equation is our output equation. So whenever you are dealing with a system which is given in discrete time, its state space model can be calculated in this way. Now let's take an example of a system which is given into us in the discrete time, whose transfer function is given to us, and how we can calculate its state space model in the discrete time domain. So let's take an example here. We have to construct the state model in discrete time domain for a system which is characterized by the Z transfer function. The transfer function of the system is given to us in the Z transform form. In the Z domain, it is given to us. So how we can construct the state model in the discrete time domain? Now there are two ways. First is through the signal flow graph and second is through the block diagram. Okay. So first we will do with the signal flow graph. Now let us convert this Z transform, the transfer function given to us in a form. Take out this Z cube common. First just multiply this, we will get 10 Z plus 4 upon multiplying this we have 3Z plus Z is 4Z plus 3. So it will be 10Z plus 4. Now take this Z cube common. And here take Z common. So it will be 10. If we take multiplying this 10 inside and taking Z as common, so it will be 10Z plus first it is 40 upon here Z cube common, so it will be 1 plus 4 Z minus 1 plus 3 Z minus 2. Take Z here common, it will be 10 Z, taking Z cube common, so it will be minus 2 plus 40 Z to the power minus 3. So this Z cube and Z cube, they are cancelled out and we have converted this transfer function in the form okay. So this is converted into the inverse of Z or in the form of unit delays. Z minus 1 is a unit delay. So we have converted into the delays form or we have converted into the negative powers of Z. Now using our first method, signal flow graph. So let's draw the signal flow graph for this transfer function. TZ is what? YZ upon UZ, that is output upon input. So cross multiplying this, we will get now through this we can get an idea that how many delays we have to introduce in the signal flow graph. Here we have the highest power of Z as minus 3. So there will be 3 unit delays. So let's draw this. It is our input and then we will have 3 unit delays and this is our output. Then first we will have, this will be our x3, x2 and x1. Then here x3 we will have z minus 1. Here also we have z minus 1 and here we will have z minus 1. These are the 3 unit delays and x3, x2, x1. These are the 3 state variables. Now let's multiply this. You will get uz 10 raised to the power minus 2 plus 40 z minus 3 uz equals to yz plus 4 z minus 1 yz plus 3 z minus 2 yz. We have to take in here 3 state variables. So first we will multiply this x3 as there are So here we will have our loop, that is x3, and it will go here. Now from x2 we have another feedback loop. So these are the two negative feedback loops, and then we have, this is x3, z minus 1, z minus 1, 3 unit delays were there, and this x2, it is here multiplied with 40, and here it is 10. So this is the signal flow graph of this system. Now through this signal flow graph we can write the equations. This is x3, so this will be x3k plus 1, taking the output of the delay elements. So output of this delay element is x2k. Now input is x3, this is x1k plus 1. We are taking the output of the delay elements as the state variable. So we have x1k plus 1 equals to x2k. Here x2k is the input to this unit delay, so it will be x1k plus 1. Then we have x2k plus 1 equals to x3k, and x3k plus 1 is this input uk minus 4x3 minus 3x2. You can see here that at this point u is coming, then minus 4x3 and minus 3x2. So this will be equals to x3k plus 1, that is the input to this unit delay, and the output of each unit delay is our state variable. This is x3, output of this unit delay is x2, and output of this unit delay is x1. So x1, x2, x3, these are the state variables. So we will write the equations like x1k plus 1. This is x1. So input will be x1k plus 1, and this is x2. Now this here output is x2. So input will be x2k plus 1, and this is equals to x3. Now x3k plus 1, here output is x3, so input will be x3k plus 1, and it is equal to the sum of these three inputs. So we have written the equations. Now through these equations we will derive the state model. So state model will be, this was our state space equation. So here we will write the coefficients of these three state variable. x1k plus 1 is x2k. So only x2k coefficient is 1, rest other will be 0. x2k plus 1 is x3k. So its coefficient will be 1 and rest will be 0. x3k coefficient of x1 is missing. So here we will write 0. Coefficient of x2 is minus 3. Coefficient of x3 is minus 4, and coefficient of uk is 1. So only here we will have uk and rest are 0. So this is our state equation. Now for output equation we will write the equation for the output. Output was yk equals to, here we have yk, so yk will be this 40x1 and plus 10x2, this 40x1 plus 10x2k here also x1k, and x3k is missing. So yk will be 40, 10, 0, x1k, x2k and x3k. So this is our output equation. So we have derived the state model from this signal flow graph. Okay, so whenever you have to obtain the discrete time domain state variable analysis, and you have to use the signal flow graph method, then convert the transfer function in the powers of z to the power negative powers of z, and in the negative powers you can use the unit delays and can easily draw the signal flow graph and write the equations for the signal flow graph, and through those equations you can derive the state model. Now the second method is to use the block diagram. So let's study the second method. Using block diagram also you can derive the state space representation in the discrete time domain. Again, the transfer function given to us is nz plus 4 upon z plus 1 z plus 3. Multiply this. Now for this block diagram technique, you have to convert this transfer function into the partial fractions. In signal flow graph, we have converted the transfer function into the negative powers of z. We have taken common, and then the numerator and the denominator polynomials, they are converted in the negative powers of z. Here we have to convert the transfer function into the partial fraction form. So tz equals to, partial fractions will be, so these are the partial fractions. How we can get it? We can convert it into a upon z plus b upon z plus 1 plus c upon z plus 3, and then we can derive the value of a, b, c. A will be 40 by 3, b will be minus 15, and c will be 5 by 3. So these are the partial fractions of this transfer function. Now we can draw the block diagram by using these partial fractions here. So this is our input, because here we have three partial fractions, so there will be three delays here. This first block is for 40 by 3, this first part. Then second part is for this second, the second part of the block diagram, and the third part is for this third partial fraction. The output of each unit delay will be our state variable. Here we have plus minus plus minus. This is our input u. This input has been given to each of the three parts, and the output, it is also summed up. The output of this summing point is y. You can see here x1 for this unit delay 1 by z, because it will be z to the power minus 1 multiplied with 40 by 3. Here it will be minus 15 multiplied with 1 upon z plus 1. This plus 1, it will have minus 1 here, and this is the unit delay. Now for this third part, here we have minus 3 and multiplied with this 5 by 3 and the unit delay. So this is the block diagram for this transfer function. Now using this block diagram, we can write the equations. So let us write the equations for this. Here the output of this first unit delay, because the output of each of the unit delay we have chosen it as a state variable. This is x1, so its input will be x1 k plus 1. This is x2, so its input, the input of this state variable will be x2 k plus 1. Of this it will be x3 k plus 1. So x1 k plus 1 is what? Uk. Now x2 k plus 1, it is uk minus of this. X2 is coming here, so it is minus x2. Okay. So x2 k plus 1 is uk minus x2. x3 k plus 1, again uk is coming here, and this is minus 3x3. So x3 k plus 1 is uk minus 3x3. And our output yk, it is 40 by 3x1 minus 15x2 and 5 by 3x3. Now using these four equations, we can derive the state model. So our state equation will become x1 k plus 1 is uk only. So here we have 1 and all the coefficients will be 0. Then x2 k plus 1 is uk minus x2. So x2 will be minus 1, all will be, and uk it is 1, x1 and x3 will be 0. x3 k plus 1 is minus 3, x3 and uk is 1, rest other will be 0. So this is our state equation. Output equation, we can use this equation for that. This is yk equals to x1 is 40 by 3, x2 coefficient minus 15, x3 coefficient 5 by 3. Here we have 5 by. So this is our state equation, this is our output equation, and combinedly they represent the state space model in the discrete time domain. So here we have studied that how we can do the state variable analysis in the discrete time domain. Whenever the system is dealing with discrete time signals, then its state model can be represented in two ways, using the signal flow graph technique also and using the block diagram technique also. We can calculate or we can derive the state space model. So I hope this topic is clear to you. Thank you.